So, Assalamualaikum and very good day. So today I'm going to show some simple calibrations of FBG to measure the temperature. So what I'm going to do now, I'm connect the FBG with the interrogator. So interrogator connect with a computer and they will show the FBG readings. So at the moment, so if I can show the value here, now we have 3 peaks. These are 3 values here, different value for 3 different location. So if you look at here, what I nampak tak? Ambil ni. So if I can show you here, so we have 3 FPG, 1, 2, 3. I don't know which one is which one is which. But never mind. So this is different FPG. Was a different wavelength value. So two attached with the structure, and the other one is not on the structure, so it's hanging outside. So we're gonna dip inside the water, and we're gonna heat the water. Okay, so we're gonna see what happens. So okay, so we're gonna take data for every 10 seconds. Okay, so we're gonna take data for wavelength every 10 seconds. At the same time, we're gonna take the value for the temperature using the temperature sensor. So this is simple calibration. We're gonna calibrate the value from the room temperature until it's 100 degrees. Okay, so let's see. Okay, so finally we plot the results for the temperature versus the wavelength for all FBGs. This one is FBG1 and FBG2 and FBG3. If you can refer to the figure here, okay, this is actually the structure that we paste the FBG on this steel structure. So FBG number 1 and FBG number 2 and FBG number 3. Number 3 is special, doesn't bond on any structure here, only FBG1 and FBG2 with the structure. So we assume that we predict by hypothesis that this should be different uh, gradient for all 3 value here, especially if you compare number 1 and number 2 with number 3. But with the results, we can see that the gradient or the curve is the same. I mean, 0.01 and this is 0.0115 and 0.0107. Let's say basically the same value. Not much different in terms of the gradient or the curve. This telling me that if you paste on the structure or it just hanging, will be the same. But if you want to know the temperature of the object, better we paste on the structure so that we can actually detect the temperature of the structure. I want to discuss about the theoretical equation, which is if you can refer to the equation here. So this is actually the theoretical equation that most of the researcher and engineers like me use to convert the wavelength into the parameter that we want to measure, either temperature or the strain. Because in the equation there is both of the parameters is involved, which is temperature and strain. For control room, which is there's no temperature change, so we can just make sure that we just assume that this one is 0, this part is 0, and then we only left these mechanical parts, which is a strain part. But for the experimentation, we look at the temperature variations, and then the strains, we assume that it is no changes, it's fixed the value. If we can, if for this equation, if we can add the value, I mean put the thermal expansion and then the thermal optical coefficient put in the equations, okay, and then we move the wavelength to this right side of the equation, so it becomes something like this. So it will become 0.011 times the temperature delta T, temperature change. This one is wavelength change, plus the this one is actually 1 minus strain optic constant, which is 0.22 for normal fiber optics. If we times this one with the center wavelength of the FBG, the value will become 1209 times the strain value. So if you look at this equation, it's actually a linear equation. Y mx plus c, okay, which is the y is actually y-axis, which is the wavelength change times the gradients of the curve, and then this is actually the x value, which is the temperature change. If you can plot again the results in terms of wavelength change, delta lambda and delta t, so it becomes something like this, and then we generate we do curve fitting, so we can find these equations. Yes, it's actually follow the theoretical prediction. Y equal to the gradient 0.01 x, which is the delta t, plus this actually the strain part. So we have the strain value here, although we claim that actually it's fixed. Yes, it fixed, but it have the value. It had a value. For 1540, 1545, it have the same. It have some values here. And then for the 5050, the one that hang, also we have value, but it's actually just. But it's actually the value very very small, very very small. If you can see at the beginning of the measurement, there is a delay in terms of temperature raise here. The same with this one. Remember that this one FBG1 and FBG2, they are actually pasted on the structure. And then for the FBG that hang without any connection to the structure, it don't have any delay. So just straight away the wavelength change move up with the temperature change. So this is the difference between the one that hang and the one that actually bond to this structure. Okay, so uh, that's it. That's it. So if I can uh, convert the equation in terms of picometer, so the results will be delta uh, wavelength equal to 11. If I can put the equation in terms of picometer, so this one become 11 times the temperature change plus 1.209 microstrain. Okay, so in other words, the temperature sensitivity is 11 picometer over the degree C, and the strain sensitivity is 1.209 picometer over microstrain. So for each 1 microstrain is equal to 1.209 picometer. Okay, so yes, actually the results showing in agreement to the theoretical value. So I'm quite happy with this one. So we're gonna do some the actual value that we can use. We can calculate with the FBG in actual application. So that's it for the experimentation. So thank you very much. That's all I want to share. So see you in my next video. Thank you very much for watching. Assalamualaikum.